Okay, let's turn next to the confidence interval for a population proportion. So in this case, we have only a sample, but it's a yes-no. So for example, we did a survey and we asked the students, do you go to the gym, yes or no? And then if we got a certain proportion, like 30%, we want to infer from that sample proportion on the true population proportion. And let's just review again a little bit what we had. So the confidence interval for the population mean, and I write it mu, for the population mean. So we wrote that as, so for example, maybe that's easier, I'll just say, okay, the 90% confidence interval we have written as our sample mean, which was a continuous variable, plus minus, and then the t-score, where we have 5% in each pocket. So I just write here again 0.05, and then we need to know the degrees of freedom times whatever standard error we had. Okay, so let's call the population proportion pi. So now, and I just already write you what the answer is. So the confidence interval for the population proportion pi, and let's say again we want to construct a 90% confidence interval, that is written as the estimated population proportion. I call that p hat. So in our survey, let's say if you had 30 students and I asked them what percentage of you go regularly to the gym, and let's say 40 said they go to the gym, so then the estimated proportion would be 40%, if 40% said out of the 30. So if 12 out of the 30 said we go regularly to the gym, that would be 40%. So, and then we do plus minus, and now, surprise, we use the z. We never use the t. And then we find the z-score, where we have 0.05, so we don't need to worry about degrees of freedom. And we have the standard error. But the standard error for a variable, which can only be 0 or 1, and you know that's a Bernoulli variable, then the standard error is written as the square root of the estimated proportion times the basically failure proportion, how many students do not go, what percentage of the students do not go to the gym, divided by n. Okay, so that is what we will basically derive now, or look at it a little bit closer. Okay, so but let's just start again with remembering that a variable, a binomial variable, something that can only have values of 0 and 1, like a coin flip example or the spinning wheel example. Let's say if you spin a wheel, there's a 20% chance that you win something, and an 80% chance that you lose something. And here you see two distributions. One is the distribution if you spin the wheel always 10 times. It doesn't really look super normal, right? Here to the right, you see the binomial distribution when the n is equal to 100. And the second panel, when the binomial distribution is based on always a sample size of 100, it looks much more normal. So that means we need to first check for a certain condition that we actually can use the normal distribution. And that condition is that, so that is the rule of thumb, using the normal to construct confidence intervals for proportions. So before you can construct a confidence interval for the population, proportion pi, make sure that the following two conditions holds. First condition is that n times the estimated proportion needs to be greater than 30. Okay, let's assume I have n equals 30, and I ask this, let's say those are students, and I ask them, how many of you go to the gym? And let's say the estimated proportion was 40%, so 0.40. And the estimated proportion of those who do not go to the gym was 0.6. Okay, so in this case, the first condition holds because 30 times 0.4 is 12. Okay, so that works. And of course, 0.6 times 30 is 18. So both conditions would hold. And I can proceed now with estimating the confidence interval. But let's assume we have a situation like this. Only 20% said they go to the gym, whereas then 80% do not go to the gym. So now the first condition is 20% of 30 is 6. This does not meet the first condition that n times the success probability needs to be greater than 10. So in this case, we could not use the normal distribution as a component of the confidence interval construction, because the distribution is simply not normal. You know, we have more a situation like this to the left. So the binomial distribution, when the success probability is 2 and n is 10, well, 0.2 times 10, that's only 2. But here to the right, where we have a probability of 0.2, but the sample size of 100, you can see it looks much more normal. Okay, so this is the first thing we need to check, those two conditions. Is n times p hat at least 10? And likewise, is n times the failure probability also at least 10? Okay, so again, the good news is that when you construct a confidence interval for the population proportion, that you only need the standard error and the z-score. You don't have to worry about t or the degrees of freedom. And again, the standard deviation of the sampling distribution of a binomial variable is given by this formula. And when we talked about the binomial distribution, you may remember that we said the variance is equal to, may I just write it like this, p times 1 minus p, then the standard deviation was the square root of the variance, so that was p times 1 minus p, and the standard error, which is here, is simply this estimated probability times the failure probability over the square root of n. Okay, but other than that, the philosophy is very similar. So let's construct now, let's take a look at the formula for the population proportion. So the X% confidence interval for the population proportion pi is equal to the estimated proportion from our sample plus minus, and now Z alpha half times the standard error. And again, where alpha half is 100 minus x over 2. So if, let's say, x were, let's say, the 80% confidence interval, then we would have in each pocket 10%. So 100 minus 80, that's 20, 20 over 2, that's 10. Okay, or if we have a 90% confidence interval, we would look for alpha half 5%. So now, graphically, imagine a normal distribution with the sample proportion as the mean and 5% probability mass in each pocket to the left and right, so that your sample proportion is covered by 90% probability mass. Okay, let's do a numerical example. And we have a sample of 50 university students, and you find that 20% use the gym regularly. Okay, let's see where we have some space, maybe here. So now we would write, what do we have? The estimated success probability is 0.2. The estimated failure probability, and failure means the student does not go to the gym, is 0.8. And we want to know the 90% confidence interval. Okay, so applying the formula, we have to first check the two conditions. So let's do that here. Let's check condition 1. Okay, n 50, so our n is 50. So is n times p hat greater than or equal to 10? Well, 50 times 0.2 is exactly 10. So we meet that condition on the margin. So condition 1 is met. We can check that off. Well, what about condition 2? Well, that would be 1 minus p hat times n, and of course that is also equal, needs to be greater than or equal to 10. But of course now we have 0.8 times 50, so that's 40. So the second condition is more comfortably met. Either way, so both conditions are met, and we can therefore continue and use the normal distribution based on or using the z-score. So what is the standard error? So the standard error is equal to the probability of success, which is 0.2, times the probability of failure, which is 0.8, over 50. And let's calculate that maybe quickly in Excel. So now we want to calculate the standard error, which is equal to the square root of 0.2 times 0.8 divided by 50, and then we get 0.045. Actually, I made a typo here. Let's go back. You see there's a typo, 0.2 should be 0.8. Okay, 0.057. So I had here a typo. It's 0.057. And so that is 0.057. And so now the only thing that we still need is, what is the z? So because we need to have the formula for the 90% confidence interval. So that is the proportion of success, that is 0.2 plus minus. So now I need to find the z-score that gives me 5% in each pocket. So let's find this one. So let's call it z-score. And that is equal to, the formula is norm S, so norm.S inf, and it is for the 90% confidence interval. That means we need to have 5% in each pocket, so 0.05. So it is negative 1.645, but don't worry about the negative because it's plus minus 1.645. So now we get 0.2 plus minus 1.645 times the standard error of 0.057. And this is all what you see here in the solution. And if you fill in the values, you get the lower limit of 10.7% and an upper limit of 29.3%. And here in the middle, we should actually say that this is the population proportion. And we should use the Greek letter. So, like this. So, the true population proportion of all the students going to Chim is between 10.7 and 29.3, or that is the confidence that we have. So what does it again mean, the 90% confidence interval? What it means is that if you were supposed to take 100 samples of size 50, you can expect 90 times to include the true population mean or the true population proportion in your sample. So that is the meaning of it. So last but not least, so let's illustrate it again visually. So here we would say, okay, 0.2, that is our sample mean. And then we build our confidence interval around it, which covers roughly from 0.107, 10.7%, and here 29.3, so that would be 0.29.3. Okay, so I hope it is clear what the difference is now between the confidence interval for the population mean and the population proportion. So the logic is very similar, but for the population proportion, you can always work with a z-score. And you need to make sure that the condition for normality hold. And if they hold, you can work with the z-scores. Okay, so let's just stop here, and then let's have a couple of videos on some problem sets next.